All right, a warm welcome to everyone to this 19th live stream of Engineering Trainer TV. We are live from the studio here, the Engineering Trainer studio here in the Netherlands. My name is Luuk Hennen. I'm the CEO of EngineeringTrainer.com. And today we are going to have a conversation with Thijs Krijger, who is a senior engineer at Dynaflow Research Group, and we are going to talk about the topic of pulsation analysis. Thijs, it's a pleasure to have you on board. How is your day going so far?
So far, it's been a great day. It's a lot of project work, and I've been looking forward to having this discussion with you. So thanks for having me.
Yeah, it's a pleasure having you on board. You know, closing our day off, you are both in the Netherlands, so it's 4 p.m. European time, closing our day off with this live stream. Thijs, before we dive in, let me also especially welcome everybody who's watching this live stream and joining remotely. And I do invite everyone, as always, to join the chat, the YouTube chat. And I always ask everybody who is joining, and that's like a mandatory, exercise if you join one of these live sessions, to put in the YouTube chat from where in the world you are joining. For me and Thijs, it's always great to see, where people are from and to interact a little bit. And it also make sure that you know to find your way in the chat. So please, take a moment, drop a message in the YouTube chat from where you are joining in. During the stream, provide comments, share your thoughts, ask questions, and I'll make sure to have those messages surface in the conversation. And as always, I invite everybody to follow Engineering Trainer on LinkedIn or on YouTube. And in this case, Thijs, who is working at Dynaflow Research Group, everybody also is invited to join their social medias on LinkedIn and on YouTube, of course. And as a final note, I'm gonna let me share that there's also various courses on the topic of pulsation analysis on engineeringtrainer.com. Let me just share my screen real quick. Let's see. Yeah. So if you go to engineeringtrainer.com, you hit explore courses, you see the entire portfolio, and by simply searching for pulsation, you'll see several courses popping up. We also have courses, like deep dive courses, but also more introductory courses. We've also learned that there are many people not doing maybe the exact analysis, but having to digest a report that was written on this topic. So we also made a course on how to review a pulsation study report, which is a course available, or any dynamics aspects, vibrations. Feel free to gauge our portfolio. And for anybody joining this live stream, you will receive a 15% discount, a promotion code, through the link that is also in the YouTube chat, or by registering to this event or checking the link in the show notes of the YouTube video. Having said all of that, let's dive straight in. The live stream, we're aiming for it to run for, let's say, roughly 40 minutes, maybe some Q&A at the end, depending also a little bit on how many questions are being dropped during the conversation. But it gives you some idea on the timeline that we're going to pursue. We already see some people joining in. We've got people from India, which is amazing. We've got people from Texas. Thanks for sharing, Ryan and Ganesh. We also received the question, is this webinar being recorded? Yes, it is. It is a YouTube live stream, meaning that the whole video will be part of our YouTube channel. If I move over there, in our YouTube channel, if you go to live, you will see all our live streams that we had in the past, and this one will also be shown there. Robert, thanks for sharing, joining in from Houston. Having said all of that, Thijs, you are joining in the Netherlands from today. Now you have a PhD in physics and over 6 years of experience at Dynaflow Research Group. I know you've been involved with numerous projects and have successfully led numerous projects addressing pulsation challenges. Maybe it's a nice starting point for you to share a little bit on what do you like about doing these types of project pulsation analyses, Thijs?
Yeah, sure. So one of the main things that I like about the pulsation, it's a very analytical project that you're undertaking, and one of the things that keeps it interesting for me, at least, is that a lot of the parameters that you're studying in your analysis don't have a linear response. Because within pulsation studies and vibration problems in general, a lot of things come down to resonances. So you might change the length of a piece of piping, and it has some effect on the pulsation levels, but well, the thing that's going to matter is, are there going to be any resonances within the system or not? Rather than just, okay, if I increase this one size, it's going to have a linear effect on the effect. So that's not the case, and that's what keeps it interesting for me.
Yeah. That makes total sense. Like a little surprise here and there, if depending on how the frequencies and the eigenmodes match. We'll definitely go into that topic a little bit in more detail, of course. Maybe let's start with sharing your screen, Thijs.
Yes.
Give me one moment. Yeah, there we go. And maybe you can start by just from the very beginning, describe what a pulsation analysis is in the first place.
Yeah. So the reason why you would do a pulsation analysis is you have a piece of equipment, for example, reciprocating compressor or reciprocating pump.
Yeah.
Those are nice pieces of equipment in that they're very robust, and they've proven themselves in the lifetime many times, but their flow profile is not constant. So there's always going to be a fluctuating flow.
Yeah.
That fluctuating flow will always have a corresponding fluctuating pressure that's also going to travel through your system, and that can cause, if those fluctuations are too high, shaking forces and then vibrations.
Yeah.
And then in the end, vibrations is always so whenever you have this kind of equipment, so either a reciprocating pump or compressor, there's always going to be some vibrations.
Yeah.
But they obviously have to be limited to acceptable levels.
Are there certain systems? I mean, you already mentioned, you have to have one of these equipments, reciprocating compressors or pumps. Are there certain systems you think that are, more prone to it? Certain specific situations, or would you say, in any case, it's really important to consider?
Yeah, so it depends a bit on the, let's say, the power and the pressure level of your pump or compressor. So especially the larger equipment produces higher pulsation levels. So in general, there's a bit, okay, for the very small compressors, the effects are going to be pretty small, and then the vibration levels are also going to be small. So there are guidelines in API standards that can be used to determine, let's say, what level of analysis would be required. And then, but they tend to, okay, for the larger systems, so more power, higher pressures, more detailed analysis is required than, let's say, at the lower power end.
Right. Before we go into that in a little bit more detail, maybe we can start just by looking at the equipment itself. I know we prepared some visuals on this.
Yes, that's true.
To just fully understand, you mentioned not a constant flow. Maybe you can elaborate on that a little bit, Thijs.
Yeah. So I'm sharing now the image of what for example, in this case, this is a reciprocating compressor. So maybe we can go over a little bit how this thing works, and how it produces the fluctuating flow.
Please, yeah.
So it all starts from this central axis here, which is called the crank axis, and this will be driven by some kind of motor, either a diesel or an electric motor.
Yeah.
So this rotates. On this side, you see there's an open, cut open part, which is a piston that's connected to that crank axis.
Right.
And that connection point is a little off-center, so that when this axis rotates, that off-center connection point rotates and causes a linear motion here of the piston.
Yeah.
So there are different parts. So what you see on this screen is, for example, a four throw compressor. So it has 4 of these connected pistons. But this kind of system can have 6, 1, 2.
All right.
There's
also one. It doesn't have to be evened out on either sides.
It is possible to make a single cylinder. It's for the forces that are acting on your crank axis will be more difficult. But they do exist.
All right. Hey, we got a question, Thijs, before we go continue from Pankaj. Pankaj, first of all, thanks for dropping your question in the chat. We just mentioned, that cutoff, or let's say limit the higher power a reciprocating compressor has, the more the system can be prone to those shaking forces. What is an indication of what is high? Is there like a fixed, certain, let's say power level, or is that depending on certain variables?
Yeah. So for example, when we're looking at this compressor system, there's API 618. It's the governing code for these types of reciprocating compressors.
Right.
And there's a table at the start of the pulsation section which gives these limits. I don't know them from the top of my head.
Yeah.
I believe for the pressure, the cutoff is somewhere around 30. So things below 30 bars are considered to be low pressure.
Yeah.
For the power of the axis, I don't know the number from the top of my head.
Yeah. That one would find in the API 618, if I
yes, that's correct.
Say correctly. All right. Yeah. Thanks for sharing, Thijs. So I mean, we were discussing the equipment. We've got those pistons going up and down, or let's say from the left to the right, based on the crank movement.
Yes.
Yeah. So how does that result into the pressure?
Yeah. So this piston is moving back and forth inside a chamber, and connected to that chamber are valves, and those will be check valves, so they will only allow flow in one direction.
Yeah.
And as your piston moves, it will compress the air or gas that's inside the cylinder.
Yeah.
And then once the pressure becomes higher than the discharge side, air will flow out of the cylinder.
Right.
And then until the piston is all the way at the top, and then it'll start reversing its direction. It'll decrease the pressure within the chamber, and then the valve on the other side, on the suction side, will open, and flow air or gas can enter the chamber again.
Yeah. Yeah, I'm visualizing it as, based on my knowledge from, let's say a car engine, which is kind of like the reverse, where the cylinder drives the crank axis, and here the crank axis drives the piston.
Yes.
But it's somewhat similar, I would say. Yeah.
Indeed. I mean, the process is indeed the movement of the pistons and the compression and the expansion of the gas are similar, but indeed in the car engine you use the expansion of the gas to move your piston, and here we're using movement of the piston to compress the gas.
Yeah, exactly. I like, maybe we can zoom in a little bit more to this, just for everybody to fully grasp it.
So I've prepared this nice schematic. So on the left side you see this crank axis with the connection point to this rod, which connects to the horizontal moving rod of the piston.
Right. And where would the check valves be in here?
So the check valves are here at the top. There's one on each side of the piston in this drawing. So those are what we call the suction valves. So they're on the suction side, and they open to let gas into the cylinder. And here at the bottom you have two more check valves, and they will open to let gas at a high pressure escape from the cylinder into your discharge piping.
Right.
What you can also see here is that there's these check valves on either side of the piston, so that you can compress gas both when the piston is moving to the right, but also when it's moving back to the left.
So in either of those movements, the piston moving to the right or the left, it pushes out like the gas into the pipeline one way or another.
Yes. So this is possible. This is what we call let's say a double acting compressor. And then indeed it moves on in both moving to the right and to the left, it'll produce flow. You also have single acting compressors, and those can be either the head end, so the far side, or the crank end, and depending on the valve or the compressor body, those can be separate process lines connected to the head and the crank end.
Oh, all right.
But you also have compressors which only have one operating side, and most of the time that will be the head end.
Got it. Hey, you mentioned various times, the word compressor and the word gas. Does this also hold up for liquids?
Yeah. So for liquids, the same principle applies. So for reciprocating pumps, we will call them then rather than compressors. But the same basic principle holds true, and that you also have these check valves and this piston moving back and forth to compress a volume up to a certain pressure, and then expansion when it moves back. But so for liquids, because the compressibility of liquids is much lower than for gases, that there are some design changes. But for let's say the basic general principle, the operation mode is very, very, very similar.
All right. And then how? I mean, so we're talking about reciprocating equipment, which is this piston. I mean, obviously there's also regular pumps, which have the rotating blades. But like, do you need to do a pulsation analysis for those equipments as well, or is it typically really related to reciprocating equipment?
So those are so the API 618, for example, is specific to reciprocating compressors.
Right.
There are also pulsation analyses that you can do for different types of compressors or pumps. But in general, those produce lower variations and at a higher frequency. For example, there's also screw compressors. which so they operate on a different principle where you have two screws that have one male and one female side, and they rotate into each other, and then there's a pocket of air that will also be compressed as the axes turn. So these typically operate at much higher frequencies. So they will also produce pulsations at higher frequencies, which can cause different types of problems that then you need to check for. Because those higher frequencies might excite your breathing modes of your piping rather than the beam modes.
Breathing modes as in the shell.
Yeah.
All right. Let's not go into that too far. It sounds like an interesting topic, though. So how do we segue from we now have the equipment to how to do a pulsation analysis? Like, maybe you can elaborate.
Yeah. So you can calculate what would be the flow that comes out through one of those cylinders, and that will look a little bit like this graph that I'm showing here.
All right. What do we see here?
Yeah. So on the horizontal axis, I'm showing the rotation of the crank angle, the crank axis.
Yeah.
So from 0 to 2 pi, so that's one full rotation. And then there's the blue line would be the flow of gas in and out of the compressor chamber if there were no check valves.
Like the dark blue line. Yeah, as in basically, the piston moving back and forth and pushing.
Yeah. So if there's no check valves, then there's just the volume that you're displacing within the cylinder, and that moves. So let's say air goes into the cylinder and moves out of the cylinder, and then net there's no displacement over time.
Yeah, exactly. Yeah.
Now, because we have these check valves, we get this compressibility effect, and there's going to be flow either through one side or the other side of the suction or the discharge side of the compressor.
Yeah.
So what happens is you start moving your piston. We're starting in this graph from, let's say, the furthest position. So we have compressed and we're moving back to expand the gas again.
All right. Yeah.
So it moves a certain distance until the pressure within the chamber reaches the pressure at the suction side.
Yeah.
And once it becomes lower, this check valve will open, and then you have this sharp step to the movement of the piston, which will be the displaced volume at that pressure.
Yeah, that is the check valve opening, that jump there.
Yeah, and then this green line shows, let's say, that the gas moving into the compressor cylinder.
Right.
Then when we got to the other side, that valve closes, so there'll be no flow going back out.
Yeah. We see the green line.
Staying
at zero.
Staying at zero, yeah. And then the red line will show the flow out of the cylinder.
Right.
So what we call the discharge of the compressor.
Yeah.
And then basically the same thing happens. So we start moving the piston back, compressing until the pressure within the chamber reaches the pressure at the line side, the discharge side.
Yeah.
At which point that check valve will open and we'll get this sharp step, and then a flow pulse.
Yeah. So we end up with the green and the red one in the actual system.
Yes. Yeah. So you'll have the green one, which acts on your suction piping. So from the flow in the suction piping will look like this green graph, and the flow on the discharge piping will look like the red graph.
Yeah. So that's an interesting point. Like, I never really realized you're not only providing, let's say, pressure pulsations, like pulsation waves into the system at the discharge side, but you also are at the same time doing suction, like expansion waves into the other side. Is that correct?
Yeah, indeed. So indeed, on both sides, both the suction and the discharge side, you're going to have a fluctuating flow.
Yeah.
Yeah, and this, so this exact shape of or the amount of compression, that depends on some factors of your gas composition. Let's say how compressible it is.
Yeah.
It depends on the volume of the cylinder. So that will be the diameter and let's say the movement, how far it goes up and down.
Yeah.
But also didn't show that before that much, but there's always some some volume that the piston doesn't sweep.
Yeah.
So basically there's some volume that does not get compressed. So and then the ratio of, let's say, the compressed volume and the non-compressed volume determines also how much compression can take place.
Yeah, that makes sense. Yeah.
And of course, the amount of compression that actually needs to happen in order to reach your discharge pressure. Also determines the shape of this profile.
Yeah. Like the settings of the check valves, or no, those open automatically. Yeah, the value of the discharge pressure. Yeah. All right. Like I know in this next slide you have like a similar plot, but then on a time line of multiple peaks.
Yeah.
So maybe you can share a little bit what we see here, Thijs.
Yeah. So if we look at this this graph on the right, will match with the red graph that we showed before, where now it's, instead of just the one revolution, it's just the time. So as it keeps rotating, you keep creating these kind of pulses. In this case, could match with your discharge side.
Yeah.
And what you can see then is there's for long periods of time there's zero flow, and then there's a peak in flow rate.
Yeah. So the majority of the time in these systems, or maybe not the majority, but there's a significant amount of time where the actual flow, if you would measure it, would be zero in the line. It moves in pulses like this.
Yeah. So at least at the outlet of the compressor.
Right.
That's true. And then, I mean, if you have a longer system, this might stretch out a little bit.
You mean the waves are like, say, distorted and reshape a little bit as it goes into the system.
Yeah. But indeed, so and then, okay, if you would take the time average of this graph, that would be your steady state flow rate that your compressor or pump delivers.
Yeah.
But indeed, in reality, it is okay. So at the exit of your equipment, there's going to be zero flow for quite a period of time, and then a spike that's significantly above your steady state flow rate.
Yeah. Hey, and okay, so we have these pulsations, not a constant, like an actual constant flow, especially at the discharge location of the reciprocating compressor.
Mm-hmm.
Why is this, like, why do a pulsation analysis? Like, what is the the problem, the failure modes that are associated with these pulsations then?
Yeah. So one step before that, I think, is if you have these kind of fluctuating flow rates, then you also have to have fluctuating pressures.
Right.
Which is shown on the left graph here. Just, okay, you have your baseline of pressure, and then you have fluctuations on that pressure level.
Yeah, that's a fair point. Like we were discussing flow thus far, but you will, because you have these peaks in flow, you will also have these peaks in pressure. That's what.
Yeah, and those peaks in pressure can cause some kind of shaking forces on your system as they are traveling through your piping system. you can have shaking forces that scale with the pressure differences between elbows, for example. So if we look at this example of a piece of piping, where we have if we look at the pressure at node number 10 and node number 20, and they could match with, for example, the black line for node number 10 and the red line for node number 20. Then you see both of them fluctuate over time. And if we look at the difference between them, it will look something like this. So here you can see, these fluctuations themselves might be much higher than the pressure difference. But just because there is some timing delay for a pressure pulse traveling, there will also be some pressure difference between the two elbows.
You mean the pressure peak hitting or being at the location of one elbow and not yet at the other one, and like that little difference or that difference causes a pressure difference.
Yes. Yeah, and that pressure differences will set up a force difference. So if you have a piping system that's under, let's say, static pressure, you always have, the pressure creates a pressure thrust at one point, which is always balanced on the other side. But now, because we have constantly fluctuating pressure, and it's not fluctuating at all points at the same time, we're going to have unbalanced forces, and that will so they scale with the pressure difference between the two elbows and the internal area of the piping.
You mentioned the word unbalanced forces here in your slides. Not too long ago, a couple of weeks ago, I had a conversation with Mick Bouwman, one of your colleagues actually, about water hammer phenomena in industrial piping systems, and there the same unbalanced forces also came up. Is it the same thing, and does it act in the same way? Like there we were talking more about it like really hammered the elbows, but are we talking about the same thing here, first of all?
So I think if you look at the physics behind it, the thing that causes the shaking forces is the same thing.
The pressure difference.
Because it's going to be a pressure difference, but the effect of it is going to be quite different. Because indeed, with the water hammer, it's the shock load to your system, and then there's going to be a response of your piping system. But here, because of every rotation of your crank axis, you can have another pulse. So this is something that's going to, as long as your machinery is running, it's going to keep on producing these pulses. So if you have this kind of pressure differences and shaking forces, this is just going to be going on the whole time your system is operating. So there's going to be these shaking forces will cause some level of vibration in your piping. But because that's going to be acting all the time, you should assess that for fatigue related damage sources.
Right. Yeah. What are typical frequencies? I'm just like so water hammer, one-time event hammering those elbows. Here you say it's more of a fatigue, like a constant ongoing shake. What are typical frequencies, Thijs?
Yeah, so the frequencies for reciprocating compressors are typically in the order of, let's say, around 10 hertz. I mean, there's higher speed, there's some lower speeds, but roughly that's the order that we're talking about. Now, besides that running frequency, if you have multiple cylinders that are firing, let's say, at different times along the rotation of the the axis, you could have multiples of that.
Yeah.
And also, if you have this double acting thing, you also have 2 pulses for each rotation. So then you have a doubling of that frequency as well.
Yeah.
So that's the order that we're talking about, and I think it's the next slide as well. If we're assessing fatigue damage, and we're looking at a compressor system, and if we're talking about order of like cyclic stress in the order of 10 hertz, then you're going to reach around 1 million cycles within a day. So it's going to be, so we're always like, if we're doing some assessment of the stress levels, it's always going to be against what they call the fatigue limit.
Right.
So the level of cyclic stress that you can have for, let's say, infinite amount of cycles. Because you will always reach a very high number of cycles within a few days or weeks.
Yeah, that makes sense at those frequencies.
Probably also good to know for people looking at these kind of systems is indeed, so okay, if you're analyzing something like this, a system that's in use, it's probably, and they have observed vibrations. It's something to be cautious about, that so if the vibration levels are problematic, that you expect failure within a short time frame.
Yeah. Or like, I'm just thinking out loud now, if you see it happening and it happens, it's been all going on for a couple of days, you kind of might assume that you're okay within the fatigue limit.
So for a couple
like,
of days,
I wouldn't recommend that though.
I wouldn't be too sure, but if the system's been running for a couple of years and it hasn't suffered any fatigue damage, then
still, good practice and good hygiene to make the system more increase the integrity of your system. But conceptually, you almost have to be safe compared to the fatigue limit.
Yeah.
Hey, received a question from Pankaj. Pankaj, thanks for sharing your question in the chat in YouTube. The question is about the shaking forces, Thijs. Does the force reverse in direction in the elbows? Can you shed some light on that?
Yeah. I think it's a very good question indeed, because the answer is yes. It does reverse. So if we're looking at, let's say, the effective force on this straight section, then as long as the black line is above the red line here, the force is going to be in one direction.
Right.
And while the black line is below the red line, is going to be in the other direction.
Yeah.
So it will actually be moving back and forth. So if this is the result of the pressure difference, then also the force will show the same profile, and it's oscillating around zero, positive and negative direction.
Yeah. So it isn't like those other graphs where we saw those positive pressure pulses in the system. It's not like a short hammering in one direction, but it's as you say, an oscillating wave around zero, the force over time.
Yeah. Yes.
All right. Thanks for elaborating on that. And again, Pankaj, thanks for dropping your question. A question that I have is, now obviously you already mentioned the API 618. We now discussed the failure mode. Like, how is that code set up, and like what checks are involved in doing a pulsation analysis?
Yeah. So the 618 has different steps that you can take, and it also has different what they call design approaches.
All right.
And the design approaches stem from different philosophies of solving vibration issues. So historically, there used to be a method that focused almost completely on only the pulsation levels. And you would put a lot of effort in reducing your pulsation levels, and then the rest of the system would be okay.
What do you mean if you say pulsation levels? Do you mean like the pressure amplitude or the frequency or the width?
So in that case, I mean the amplitude of the the pressure fluctuations.
Got it.
So the code specifies some limit, some allowable fluctuation of your pressure.
Yeah.
And that is a function of different things. For example, the frequency, the diameter of your pipes, and the wave speed.
Yeah.
But there's that's one way of looking at it. But in the end, vibrations are always going to be a combination of an acoustic system that interacts with the mechanical system. So you can try to solve your vibration by solving your acoustics, but you can also solve vibrations by solving the mechanics of your system.
All right.
So maybe you keep your pulsations and your fluctuating forces a little bit higher, but as long as you ensure that your system is stiff enough that it doesn't overlap with any mechanical resonances, for example, then you can still limit your vibration levels.
Yeah. So meaning you accept that the pulsation levels are maybe somewhat high, but because the system is able to deal with it, it's still okay.
Yeah. So indeed, there's in the current version of API 6.18, there's two design approaches left. That's design approach 2 and 3. Historically, there used to be design approach 1, but it's no longer allowed since last year's edition of the code.
All right. What was that? What was that one then?
So that one focused only on the pulsation levels.
Okay. Yeah.
And that one was historically only used for what we talked about at the beginning, the low power, low pressure systems.
Right.
And it's a bit of an empirical way. Okay, you size your dampening devices sufficiently large, then probably you won't have issues with vibrations.
Yeah, maybe you can sort of jump in again here. You mentioned dampening devices. Now, maybe you can elaborate a little bit on what you mean by that.
Yeah. So we have them on the screen now. So what you see here is this a compressor, and visible there are two throws, number 1 and number 2. So within these chambers, you have the piston moving back and forth, basically in and out of the screen in terms of the direction. And then on top and below, you have the discharge and the suction sides.
Yeah.
And you see these large volumes, these large bottles.
Yeah.
And those are typically used to dampen the pulsations that are produced. So by allowing your flow to go through a larger volume, you dampen the level of the pressure pulsations.
Yeah.
And so the API has different checks that that you have to perform if you do a pulsation study.
Yeah.
And some of them apply to the compressor itself. So there's a pulsation level at the compressor flange, which would be the inlet and the outlet of the compressor.
Yeah.
And that one is mainly to ensure that your valves and the internals operate within acceptable limits.
All right.
Then there's for the pulsation suppression devices, so the PSDs, which are these bottles.
Those dampeners,
Yeah. So there's a shaking force check to ensure that you don't shake your pulsation dampener and cause fatigue damage within the pulsation dampener.
Oh yeah, like same forces also happen within the dampener then I guess.
Yes. Yeah, exactly. And then there's also a pressure drop check for the pulsation dampener, which is performed to ensure that you have an efficient system. So if you would have too large a pressure drop over your pulsation dampener, it comes at the cost of the efficiency of your system.
Yeah, you're losing pressure at the device which is meant to create pressure in the system.
Yeah, exactly. So your compressor, you want to increase the pressure, and then you're losing it again at the at the dampener.
It's interesting though. Like what I find remarkable is that the API has a check on that. I mean, if a supplier or buyer wants to have an inefficient system, if they are able to make a business case around that, why like the API says you can't, like, it's a push for efficiency, I guess, on their end. Like, what are your thoughts on that?
Yeah, so there's in this API committee there's also end users. So I'm sure they have their input there as well. They prefer these kind of things. Also, there is a clause that you can, in some cases, in discussion with the end user and the person or the company delivering the compressor, arrive at a system that does have excess of pressure drop over the pulsation dampeners.
You can deviate.
Yeah, and especially if you have a compressor system that has to operate not just for one type of gas, but for multiple gases, or other differences in operating conditions, it might be impractical to design a system that has that pressure drop met for all different operating cases. In those cases, probably aim for having it be as efficient as possible for the case that's the most likely, or the system will operate at the largest part of the time.
Just to segue back a little bit, like, you mentioned those 3 checks. One is pulsation level, and before we introduced the other 2, you kind of moved into like what we are seeing here, what a dampener even is. So maybe you can continue like on that, like, these 3 checks are those the, let's say, colors that you are referring to here, or are those different things?
So the colors I can overlay a little bit on the image. So this is also to indicate where the parts are on the system. So the compressor check applies to the compressor, and then the pulsation bottles are here at the top and the bottom. And then in red would be the connected piping. So that's your line side piping, for which you also do a pulsation level check. And then the pulsation levels within this piece of piping, there's an allowable for that defined within the API code, as well as a shaking force check.
Okay, so those level 1, 2, and 3 are not the same as the green, yellow, red here.
No, indeed. So historically, the level 1, maybe we shouldn't be talking about it since it's no longer allowed. But so that would focus mainly on only the compressor and the dampener, and not look that much at the piping. But for the design approach 2 and 3, you also look at the piping, and you're also going to be looking at the mechanical response of the piping. So either in design approach 2, you're looking at the mechanical natural frequencies of your piping, and they have to be sufficiently separated from the excitation frequencies that are caused by your compressor. And then in design approach 3, which is the most detailed analysis, will give the least conservative results. You're actually going to be doing a study on what would be the cyclic stress levels within the system.
Right. Yeah. We've got some questions, Thijs, that were dropped in the chat, but
Great.
maybe let's one is related to pipe stress, so we'll park that one for the end of the conversation. One is from Pankaj. Thanks again, Pankaj, for dropping in a question. And also thanks Robert and Luis for providing your thoughts on it. The question of Pankaj is, the Energy Institute guidelines suggest that above 12 hertz of natural frequency, a piping system is stiff. Is this sufficient? Can you state it like that? How what are your thoughts on that?
Yeah, so it depends a bit on what would be the cause of vibration that you're going to be trying to mitigate for. So if you're having a compressor that's running at, let's say, 14 hertz, it's going to produce excitations at 14 hertz, and then stiffening your system so that it's above 12 might not be enough, because you want to ensure then that it has no resonances near the 14 hertz.
Right.
So in design approach 2, what they use, the guide they use there is that your mechanical natural frequency of the piping system needs to be 2 times plus 20% above the running speed of your compressor.
Yeah. So if your compressor runs at 14 hertz, then the check of that level 2 check, the frequencies that you need to come up with are way higher than the 12 hertz suggested in the Energy Institute, I guess.
Yes.
But that would boil down to 14 times 2 plus 20%. Those are quite high numbers to remove eigenmodes.
It's indeed it's a very difficult problem to solve, which is, I think, why more people are going to that design approach 3. Where you do a more detailed analysis of what's actually the effect of, okay, maybe I'm exciting my system near resonance, but I'm modeling it in such detail to see, okay, what's going to be the stress levels when I'm doing that.
That would be a level 3 analysis, like actually going into to let's say compare the frequencies.
So you're actually gonna do the acoustic study to find what are my shaking forces, and I'm gonna apply those to my piping system, which includes all the stiffnesses of the supports. It includes the stiffness of the compressor manifold, the pulsation bottles. So in those cases, often also you need to model not just the piping, but also the steel structure on which the piping is supported.
Yeah, I know you like we yesterday when we prepared this conversation, you also shared a slide that showed a little bit those different peaks and resonances. Maybe we can jump to that one. Yeah, yes. I think it was this one.
Yeah, so I think this is a good summary as well to wrap up, maybe, because in the end, the problem is going to be vibrations, but the causes can be in either the acoustics, which are set up by the equipment, so your compressor or your pump, combined with the damper and the piping geometry, will set up acoustics, and those form your pulsation, resulting pulsations.
Right.
And those pulsations then cause shaking forces. So if we look at a plot like on the right, where on the horizontal axis we have frequency, and on the vertical axis here we have dynamic pressure. So the system might produce pulses at multitudes of, let's say, this roughly 20 hertz.
Yeah, by system you mean the equipment, or
the equipment,
not?
Yes.
Yeah.
And then you can look at what would be the acoustic modes that are possible within my system.
Yeah.
Which is what's shown on the middle graph.
Yeah.
And then kind of the overlap between those two will give you what is the actual acoustic response of the system.
Yeah. Yeah. So we're not talking about mechanical response at all here.
Not yet. Not yet. But so the next step would be to look at, okay, we have this acoustic response is going to be an input for my mechanical system.
Yeah.
So we have this pipework acoustic response from the previous slide. Then we're going to look at, okay, what are the mechanical natural frequencies
right
of the system?
Yeah.
And then if there's an overlap between those, then that will be the resultant vibration, which is in the end the thing that we want to limit.
Yeah.
So this, let's see, now in this example, you have, let's say, a high vibration around 40 hertz.
Yeah.
And this might be solved either by removing somehow or lowering the amplitude of this pulsation.
Yeah.
But you can also move away, try to change the stiffness of your support structure in order to eliminate the mode at this frequency.
Yeah. Yeah.
Which would also result in this vibration level going down.
Yeah. So if I summarize it correctly, you have the the reciprocating compressor causing pulsations, then there might be acoustic resonance, and then you get like your, let's say, pressure pulsations in the actual system, and those can cause mechanical resonance, yes or no. Let's say you have a very stiff system, so no mechanical significant movements, whether we have resonance, yes or no. But you have really high pulsations. Is that a problem? Like pulsations in itself won't cause fatigue unless anything moves. Is that an issue?
Yeah, so it could be an issue if your pulsations are really extraordinarily high. Because the system will still respond even though you're not at a resonance.
Okay.
So also if you think of your simple mass on the spring.
Yeah.
If your shaking force is large enough, even if it's off resonance, it'll still move.
Still move. Yeah.
So we can kind of summarize this maybe with some cases. So this the case you were talking about before. Okay, we have high pulsations and we can still cause vibrations even though
no resonance.
There's no resonance. There's also possibilities where, okay, maybe your pulsations are a bit lower, but you have acoustic resonance.
Yeah.
And those can cause the same thing. So you're still going to have high shaking forces acting on a system that might not be mechanically resonant.
Yeah.
But still causes vibrations.
Yeah.
The reverse is also possible. Maybe your shaking forces are not that high, but they're exactly at the mechanical resonance. Can cause large response of the mechanical system.
Yeah.
And then let's say the perfect storm or worst case scenario is, okay, you have pulsations, they have acoustic resonances and mechanical resonances, and everything overlaps.
Yeah.
In which case the vibrations are going to be very high.
Yeah. The perfect storm. Yeah. And like when it comes from a mitigation point of view, I mean, you already mentioned some. You mentioned stiffening the system, stiffening your support arrangement. That would, in any case, help, I guess, in any of these scenarios.
Yeah. So indeed, the piping and supporting stiffness will act on let's say this part of the flow diagram.
Right.
So that will indeed, you can use that to limit the vibrations. But you can also make changes to your pipework or your dampeners in order to change the acoustics of the system.
Like what kind of changes for the acoustics?
So for
diameter?
the acoustics, so the diameter, length of dampeners can be important. There's also possibilities if you have some acoustic resonances. You can use orifice plates to eliminate those. Because the orifice plate will kind of force a reflection point where you place the orifice.
Yeah, you kind of cut like a wave in half or something. That's how I think about it, I guess. Yeah,
I think that's a good image indeed.
But that would yield a pressure drop.
It would yield a pressure drop, yes. And then, of course, there's an engineering step involved in, okay, what is an allowable pressure drop, which still has the desired effect.
Yeah.
And in general, the pressure drops over those orifices don't have to be super large to get the effect of imposing the, let's say, reducing the acoustic mode.
All right. So not a very big drop, like a minor ring inside would already cause some reflections.
Yeah, and then it's just, okay, the acoustic mode that might be problematic because it was exactly at the frequency of your excitation maybe can no longer exist within the system, and then the resultant pulsations will just be much lower.
Yeah. Hey, given time, I mean, we've been going at it for close to an hour now, and we also have several interesting questions that were dropped in the chat that I parked till the end. So let's move into those questions. Like one questions I would like to bring as to finalize our conversation as well. All of those mitigation measures, especially the ones that influence the acoustics, sound pretty intense. Like, I mean, a support you can add once the system is already built. An orifice place is already much more difficult, let alone those changing those bottles or the routing. I mean, that's a challenge, I can imagine, right? You have your system, maybe something shakes when you start it up, which is alarming. Then there's no easy solution to solve the acoustics that aren't quite intense to the system.
No, that's correct. I think probably installing an orifice plate would probably be the least invasive.
Yeah.
If you have already a flange connection, you might be able to fit one in.
Squeeze it in, yeah.
Often a good place for those will be at the bottle opening, so the pulsation bottle, let's say inlet or outlet, depending on if you're a suction or discharge side. But indeed, changing the pulsation bottle, if it's already been manufactured, is often no longer an option, and then you'll try to find solutions more in the supporting layout.
Yeah. All right. Let's discuss some of the questions, Thijs, that were dropped in the chat. Again, thanks everybody for sharing your questions. They are on various topics, Thijs. So let me, we'll be shooting around a little bit. Let's see which one is a good starting point. For the fatigue check, Thijs, would you consider only stress due to shaking forces or combined stress with thermal or pressure loading? Could you comment on that?
Yeah. So I believe it's the B31.3 code. There's usually for occasional stresses, for example, these shock loads for water hammer, they have to be combined with your other sustained stresses. For fatigue, that doesn't have to happen, because the fatigue allowable. You can assess that separately from your static stresses. One difficult thing in these kind of systems is that often the things you want to do in order to solve your vibration problems are going to cause issues for your static stress analysis.
Right.
Because we want to make the system more rigid, place more supports, more guides, and then it doesn't leave much room for the thermal expansion.
Yeah.
So there is some kind of iteration usually, and some back and forth between two different teams, maybe, to get the system to a state where both the static and the dynamic stress teams are happy.
Yeah. You have to converge to a solution that works for both, let's say, load cases.
Yeah.
All right. Thanks for elaborating that. Like a follow-up question I would have is, like, when it comes to thermal and the thermal loading is also cyclic. You might have operating modes. Do you have to combine those then? Like different, does one cyclic load eat away margin for the other one?
I think it depends on the how often the thermal cycles happen. If this is like a low cycle fatigue thing, then probably you assess that in combination with your other static loads. If it's high cycle fatigue, then you would you have this Miner's rule to combine different load cycle, different fatigue cycles together to assess damage. So what you do is you calculate the number of allowed cycles compared to the number of real cycles that the system is going to see, and then the ratio, the inverse ratio of those two, gives you a number below 1, you hope, and then you can do that for multiple different cycles, and then you combine those together.
All right. Thanks for elaborating on that, Thijs. Let me jump to another question. Let's see. Considering it is a non-linear analysis, and then especially when we look at the mechanical analysis, how can friction forces be considered? Could you comment on that one, on the friction forces when looking into the detailed mechanical response?
So for example, if we look at the Caesar has some option to kind of try to approximate friction with by replacing it with some kind of stiffness constant. But indeed, it's it's not usually not an accurate representation of actual friction. But I think it's a good comment indeed that it's very difficult to incorporate friction correctly.
So that is one of the challenges when doing the actual detailed mechanical assessment. All right. Let's see. Do you typically, final question, Thijs, do you typically, or how can those shaking forces be related to displacements? Is there like, what do you even do that, and what methods are available for that?
So when we do the pulsation study, we do it in our own software, which is called Boss Pulse. And in those, you can do the let's say the acoustic part of the pulsation study within our software. And then there's an option to either export those forces to another pipe stress software, for example, Caesar 2.
Yeah.
And then you can look at the response. Okay, so these shaking forces, if I apply them harmonically to my piping system, what will be the displacements?
Right.
But we also have now coupling with ANSYS, and so we can also do that mechanical analysis of the response of the system to the forces within our own software.
All right. But you basically you need the software to go from pressure pulsations to I mean, your software was Puls, the way I know it, goes from pressure pulsations to forces, and then you need a piece of software, either yours or another one, to go from forces to displacements.
Yeah.
All right. Thanks for sharing it, Thijs. One, final set of comments provided by Robert, which I also want to share. Thanks, Robert, for joining in on the chat there. Robert says mechanical team typically wants higher running speeds for efficiency, which is problematic for piping design. If you go for 300 RPM system, that would yield, which is 12 hertz. So common and preferred speed of 300 RPM. If you would push it higher to, for example, 600 RPM, you would end up with, which is 24 hertz, which is very difficult for piping design to remove those eigenmodes, mechanical eigenmodes for those types of frequencies. I think this is what is in line with something you just mentioned now as well. That those higher frequencies, it's a challenge. So you have to look into details. Are we in the same? Is there overlap? Will there be mechanical resonance?
Yeah, and I think we haven't really covered it yet, but the story becomes even more difficult if we're talking about a variable speed compressor that can run at different speeds, because then detuning your mechanical structure away from resonance becomes almost impossible.
Yeah. So then you almost have to design for potential resonance.
Yeah.
I see.
Which is part of that design approach 3. So then, okay, we're going to be exciting at some of the mechanical resonances.
Yeah. All right. I see my camera froze somehow, but we are at the end of the live stream, so let's wrap it up. Thijs, thanks again for making the time and putting in some energy to join the conversation today and share your experience with these type of analyses. It was a pleasure having you on board, Thijs, and hopefully in the future we can do a deep dive on any other topic that you are involved with.
It was my pleasure too. Thank you.
And for everybody listening and joining in remote, whether it is live or later in the YouTube video, make sure to check out the link that was provided in the YouTube chat, or that is available in the YouTube show notes. There you will find the option to obtain a 15% discount voucher for any of the courses on EngineeringTrainer.com. Please be invited, to connect with me or Thijs on LinkedIn if you have any questions, if you are interested in any of the courses or, let's say, services that are being provided. And we look forward to having you on the next live stream, of course. Have a great day, Thijs, and have a great day, everybody.